Today we want to talk about partial derivatives. We want to look at the similarities with what we've learned before, see how we modify that to deal with functions of more than one variable, and just see how similar it is. And then we'll find out all the stuff that we already know how to do. I'm not going to tell you how to do stuff. I'm going to ask you to guess at how to do stuff, and you're going to find out that for the most part, you're going to be right. Anytime in a math class where a new thing comes along, and you can just guess at how it's supposed to work, and that's how it works, that's pretty good. That's a good design, right? That's just quality design. So think back to when we first learned about derivatives. We had y equals f of x, and we got one derivative. We're going to write it in Leibniz notation with dy over dx to remind ourselves that this is the rate of change of y with respect to x. So this is the rate of change of y with respect to x. Because there's only one variable running around, we sometimes will shorten this. Let's talk about the rate of change of y, but that's not going to be good enough. That's not going to be good enough because we're going to have more variables showing up. So we're going to have to say with respect to x. So think about two rates that we have that involve the same y. Miles, and we can have miles per hour and miles per gallon. One of them is your rate of change of distance with respect to time. One of them is your rate of change of distance with respect to gas or volume of gas. But they're both expressed as rate, miles per hour, miles per gallon. Because there's only one derivative, we get to use Newton's crappy notation. I shouldn't editorialize. Newton's definitely not crappy notation. F prime of x, which is not even Newton's notation. But we get this derivative dy dx. Now, what we want to do is upgrade not only our notation and our thinking, we're going to increase the number of variables. Let's see what we get. So now we have z is a function of x and y. Z is a function of x and z is a function of y. Instead of having one derivative, dz dx, we'll get two derivatives, dz dx and dz dy. The rate of change of z with respect to x and the rate of change of z with respect to y. We get two derivatives. Since there are two, and we just look at them in pieces, we call them partial derivatives. Two partial derivatives. We also change up our notation to remind ourselves that we're doing partial derivatives. So instead of a regular d, we write this kind of modified lowercase delta. Just draw 6 backwards with the loopy part. It's d without the kickstand and in a high wind. We're still going to call it d. We're still going to say d. But we get two partial derivatives. dz dx. The rate of change of z with respect to x. Spelled with wrong. Forgot the w part. And dz dy, the rate of change of z with respect to y. So we have two partial derivatives, dz dx and dz dy. In this case, we can't use prime notation because we have two different with respect to. Change of z, yeah, but with respect to x or with respect to y. Prime is not going to tell you. So our notation for a dz dx, if z is a function f of xy, we use a subscript fx at xy and fy at xy. This is because prime does not communicate enough information. Prime just says derivative. There's only one variable, so it doesn't matter. Derivative with respect to whatever variable you're using. But now that there are two variables in play, we got to distinguish dz dx and dz dy, df dx or df dy. We're going to shorthand and call this fx at xy and fy at xy. So we don't get to use prime anymore. Now, when we talk about it with respect to x or with respect to y, I might say it slightly differently. I might say in the x direction. And with respect to y, I might say in the y direction. We didn't really refer to derivatives in terms of direction when we had a function of one variable because there was only one direction, the x direction. Left and right is only one direction. Left is just -1 times right. So it still only counts as what? That's called the Gimli rule. Still only counts as one. This is an important thing to note because when we had a derivative with respect to just one variable, all we had was x direction. What happens when x increases by 1? But now we're dealing with two dimensions, an x direction and a y direction. What happens when x increases by 1? What happens when y increases by 1? That still only tells us about two directions. And a plane has 360 degrees of direction. But this is where we're going to start. A plane has 360 degrees of direction. We're only going to need two because a plane is just everything in the plane is made up of these two directions, some x direction, some y direction. So if we have a graph like miles, like z is miles, and our output is based on gallons of gas that we use and the distance that we have to travel. Maybe x is miles and y is distance. Then we can think of our two partial derivatives as our mileage, miles per gallon in one direction, and our speed, miles per hour in another direction. And maybe things would be that organized. If we're going this far and this many gallons, now we can see our change in distance. The thinking about rates of change isn't going to change. It's just that now we have more than one input. So we have dz dx and dz dy. That part is still the same. We have to be able to calculate partial derivatives. I'm not going to tell you how to calculate partial derivatives. I'm just going to ask you to calculate some partial derivatives. So I'm going to build a function, a nice simple function. Let's say it's 5x squared y to the third. And I want you to find fx and fy, the two first partial derivatives. Take a moment and think about how you find the derivative of f with respect to x. So if we think about how f is changing in the x direction, we're going to think about it this way. I don't care what the value of y is. I want to know how z is changing in the x direction for some fixed value of y. For any fixed value of y, what's happening in the x direction? This is the same thing that we were doing when we take a force and write it as components, right? The horizontal and vertical components of a force. So the force is going at some funky angle. I want to be able to compare it to some other force at some other funky angle. I'm going to break those forces into horizontal and vertical components, things that I can directly relate in the two different forces. We're going to do the same thing here. Forget the y, pick a constant value of y. What's the derivative of this function with respect to x? What's the derivative of the x part of this function? 2x. Everything else, we just keep constant. So I keep the 5. 5 is just a constant. The derivative of x squared is 2x. Everything that's not x is constant. So we get 10 xy cubed. You treat everything what's not x as constant. In this case, the y cubed is a constant factor, and constant factors just get carried along in our derivatives. For the derivative with respect to y, we'll do the same thing, but with x. 5 is a constant. X squared is constant. What's the derivative of y cubed with respect to y? 3y squared. 3y squared. So overall, we'll have 15 x squared y squared. So we treat x as constant. Note that in this case, x was treated as a constant, and in this case, x is included with multiplication. So we're treating x as a constant factor. And so up here, we treated the y cubed as a constant factor. It's the same way that we treated the 5. 5 was a constant factor. Observe, okay? Yay, mechanics. Let's look at another function. Let's say g of xy is x squared plus y cubed. plus 5. And we want to find gx and gy. When we're thinking about the derivative with respect to x, x is the variable, everything else is constant. When we look at that y cubed, what's the derivative of the y cubed with respect to x? 0. In this case, y cubed is a constant term, and the derivative of a constant term is 0. So the derivative gx is only going to be the 2x, and then these are just both going to be 0. So we'll just say plus 0 plus 0. We wouldn't write that. We're treating y cubed and the 5 as constant terms.
Why are those constant terms a 0 and in the previous equation they weren't constant terms? Or they
In the
weren't,
previous function, they weren't, the y cubed and the 5 were not constant terms. They were constant factors included by multiplication. It's 5 times x squared times y cubed. So those are constant factors, and here they're constant terms. It's the difference between the derivative of 5x squared and 5 plus x squared. So what would the derivative with respect to y, derivative of g with respect to y equal in this case? Three y squared. In this case, the x squared and the 5 are constant terms. Now x squared and 5 are constant terms. Constant factors just get carried along. Constant terms differentiate out to 0. We wouldn't write all the plus zeros. We're just trying to make a point. How's everybody okay? Right. Let's go with this. Let's go 5x to the 4th. This is not a big change from the previous one. With respect to x, though, I have 2 terms that aren't constants, but with respect to y, I'm only going to have 1 term that's not constant. So my hx of xy, the derivative of x squared is 2x, like before. The derivative of y cubed, that's a constant term, so that's 0. The derivative of 5x to the 4th is 20x to the 3rd. So we end up with these 2 terms. Because out of the 3, with respect to x, only 1 was a constant term. But now for hy, our perspective has changed. The derivative of x squared, that's a constant term with respect to y. The derivative of y cubed is still 3y squared. And this 5x to the fourth, that's just a bunch of constants as far as y is concerned. So we only end up with the 3y squared like we had before. G and H are the same with respect to y. The plus 5 versus plus 5x to the fourth is only going to change things at different x values. But the y is always going to look like a y to the cube, y cubed plus some constants. That's everybody okay? Mechanical bits. So much fun. Just by example. Some of you that don't mind grinding problems out, this is your kind of like today. Oh, this predicts a homework that's going to be of the format. In problems 1 through 1,000, do the thing. And you just have to do the thing 1,000 times. Like the World of Warcraft players, if they actually log off and then do their homework, this is their kind of homework. Because it's the same thing over and over and over and over again. If you bounce off of MMOs, like, oh, it's the same thing over and over and over again. Then you see the assignment says, in problems 1 through 1,000, do the thing. And you're like, oh, no. Can I still get an A in this class without doing this assignment at all? Yes. Guess what assignment I am doing? So in this case, there's 3 terms. With respect to x, 2 of them are not constant terms. The x squared and 7x to the 8th y. And with respect to y, there are two non-constant terms. Y cubed and 7x to the 8th times y. So with the derivative with respect to x, derivative of x squared is 2x. Y cubed is a constant term, so the derivative is 0. The derivative of 7x to the 8th, 7 is a constant factor, it stays. The derivative of x to the 8th is 8x to the 7th. And the derivative of y is, we're not worried about it, it's a constant factor. So we got to make sure that we can identify our constant terms versus our constant factors, so we don't zero out things when we should be keeping them, or keep them when we should be zeroing them out. So all these weird ass polynomials. Everybody the wrong impression that polynomials must happen a lot. It's like, oh no, they're just the easiest examples to come up with on the fly. That's why. Being in a math class will skew your view of the world horribly. Like most of the polynomials that you've encountered in your mathematical career have been factorable. And that's just not true. If you start creating polynomials at random, the probability that a randomly created polynomial is factorable is 0. Like, you just drop a bunch of real numbers in front of your polynomial, it's not going to be factorable. If you drop a bunch of random integers in your polynomial, it's not going to be factorable. So you get this skewed version because we wanted you to practice the skill of factoring for whatever reason. And it's like, oh, most polynomials must be factorable because most of the polynomials I've encountered in my life are factorable. But there are other polynomials outside of your experience. It's almost as if it's skewing your whole view of humanity. Maybe we shouldn't think that much about it. For the most part, everybody's like, oh, I wasn't paying attention anyway. So we take derivatives. Sometimes the x is a term, sometimes the x is a factor. In this x squared, the derivative of x squared is 0 because it's a term. The derivative of y to the third is 3y squared like before. In this third term, it has x's and y's. The 7 and the x to the 8 are constant factors, but the y is a constant term. Y is our variable part. So the derivative of y is equal to what? So we get 3y squared plus 7x to the 8. Is that okay? I'll do how many more examples? Not many, like 10 minutes. I know you were looking for like a number of examples, but best I could do is 10 minutes. I think like a professional teacher could crank out like 5 or 6 examples, but I can't answer yes or no questions with just yes or no. As y'all have seen. I'm also running out of space on this page, so the other question that you have to be thinking is, how willing are we to go on to a third page of notes? Is he or is he not going to change the page? The nice thing is this is all just derivatives, and we have all the tools we need for derivatives. That's why all these problems are so simple. Because we have all the derivatives. Derivatives is a solved problem for us. It's like tic-tac-toe. A limited number of things we need to do. In this case, I set this up so the first one is messier. What rules are we going to have to employ to take derivatives here? Chain rule. What's telling us to use the chain rule? There's sine and there's a bunch of stuff in the sine. It's sine of stuff, not just sine of x or sine of y, right? It's sine of stuff. What other rules might come into play? Trick question. There's only one other rule. There's product rule and chain rule. So if you're like, oh, a chain rule, I'm like, well, what else? Just say product rule because it has to be, because that's the only two for derivatives. Like I said, differentiation is solved. You know differentiation. It's tic-tac-toe. Tic-tac-toe, there are only 3 opening moves and 3 possible responses to those moves. That's it. Three opening moves. If you think there are more than 3, turn the board 90 degrees, and then you'll see that there are only 3. Center, corner, or side. And if you open up in a center or a corner, the game's over. Unless someone screws up. If you open up in the side, then you're an idiot. And you don't know how the game works. But if your first move is in the center or in a corner, the game is over. Unless your opponent makes a mistake. Which just means they don't understand what the game is for. You know what I mean? In which case you're taking advantage of them and you should be ashamed of yourself. Let's think of this in turn with x as the variable, qx of x and y. Here, we're gonna have to use the chain rule on that sign, but what else are we gonna have to use here? See, that was that trick question I just told you. It's definitely the product rule because there's another rule. It's gotta be product. The chain has already been taken. The reason that we have to use the product rule is that there's a function of x, 5x squared, and another function of x, sine of x cubed. There's two functions of x joined by multiplication, so it's a product rule. And the derivative of the second is going to be a chain rule. It's the derivative of sine of some junk. Right now, we're looking at that y to the fourth is just a constant. This might as well be 5x squared times the sine of 4y to the third. So I have to take the derivative of the first. That's the easy part. Times the second. Derivative of the first times the second. Plus the first times the derivative of the second. The derivative of sine of some stuff is cosine of that stuff times the derivative of that stuff. The derivative of x cubed y to the fourth with respect to x is 3x squared times y to the fourth. Derivative of sine of stuff is cosine of the stuff times the derivative of the stuff. In this case, the derivative of the stuff is derivative with respect to x. Nothing new here except for looking at that y to the fourth and just thinking that's a constant. This is also a mess. We should simplify this. This looks terrible. So I'm gonna like halfway simplify it. So I got 15 x to the fourth, y to the fourth, cosine x cubed, y to the fourth. We could factor a 5x out, but I don't really see a lot of value in doing that right now. It's not like I need another derivative. Or a second derivative, I mean, because we do need another one. Now we want to take the derivative with respect to y. What rule are we going to have to use? Chain rule, the sign of stuff, and that stuff involves y. Do we need the product rule in this case? No, you can tell the answer was no, so I would have just said, what other rule do we need, right? You got to read the whole question. Don't just read the whole question. Always be reading the whole question. We don't need the product rule here because that 5x squared is not a function of y. So as far as y is concerned, 5x squared is constant. 5x squared is a constant factor with respect to y. Five x squared is a constant factor with respect to y. I say constant factor because it's included with multiplication. So I just treat it like a constant factor, 5x squared. The derivative of sine of something is cosine of that thing times the derivative of that thing. In this case, x cubed is a constant factor, but the derivative of y to the fourth is 4y to the third. So we'll only ended up with one term in the derivative with respect to y. We didn't use the product rule because we only had one factor that was a function of y. 520 x to the fifth, y to the third, cosine x cubed, y to the fourth. Because calculus is the engineering version of a math class. That's why I think derivative went first, because it's a problem that you could solve completely right away. That's why we do that in the first semester, even though it's based on a weirder question. It's not just based on addition, it's based on finding the slope of a line. You have to secant line things close together instead of just like chop things up into slices. So if ever you're wondering why the weirder one to think about goes first, it's because the weirder one to think about can be completed mechanically in way less than a semester. Product rule, chain rule, done. All right, that's going to do it for today. Is a new round of homework that appeared that will be due on Sunday like normal. So that's it for today. I'll see y'all on tomorrow. Have a good day and thanks for playing.